kind of understanding of where they're getting their information. Okay, when I was in school, I would read a story column like that. We were talking about this revenue stuff and trying to sell a commodity. I would struggle. I had no problem with the math, but then trying to piece things together. Okay, why am I even doing this? Where is this coming from? Did somebody just throw this equation together with a bunch of numbers, or is there like legitimacy behind this equation? Okay, and what I hope to kind of shed light on for you, because there are careers that are involved in doing this, is that there's absolutely 100% substance behind those formulas. Okay, companies like P&G, Pepsi, Ford, Dana, they have analysis groups that look at this data and collect data. Okay, and then they allow that data to show them trends, and then they're allowed to use that data to make decisions. Okay. So I've got an example here that kind of embodies that idea. The question starts off as, let's see here. It says most cars get their best gas mileage when traveling at a relatively modest speed. Gas mileage M for a certain new car is modeled by that function. Okay? So what that function is going to allow me to do is say, okay, I'm picking a certain speed, and it should spit back to me then how many miles per gallon I should get when I go that speed. Okay? If you've ever, has anybody ever driven in a like a U-Haul truck or anything like that? You guys, so like when you rent a car like that, and I don't know, I haven't rented other types of cars, but like renting a U-Haul, the speedometer is a colored speedometer. Okay, it's got red, green, and yellow on it. It's like red, yellow, and green, and it's all over the place in their kind of their structure in that kind of semicircle on your speedometer. You guys know what I'm talking about, your speedometer? Okay, and basically what it does, it tells you that if you want to maximize your gas mileage, you need to keep that tack on the speedometer in the green. If it's in the red, you're going to waste gas. Does that make sense? Okay. And it's just basically showing you the efficiency of that car. So what it does, just going to give you a real quick picture here. You've got your speedometer, semicircle, right? Okay. What they're going to say is, like right here, in that region, it's got your speeds on it and all that garbage, but that region is going to maximize your fuel consumption. That region is not going to be so good to you, and these regions are going to be terrible. So you want to keep your tack maybe right there. Does that kind of make sense? In the green, so that you maximize fuel efficiency. Okay. Well, how do they know that? Okay. They know that from a model like this. Okay. How do I know when I watch a car commercial, and at the end of it, it tells me that this particular model of car gets 32 miles per gallon on the highway and 28 miles per gallon in the city? How do we know that? Okay. And because they tell you that, but they don't tell you explicitly what the speed is. They hide it. At the end of the commercial, if you were to pause it, when they flash up, like what the price is at the bottom, there's a lot of small print, and nobody reads that small print. Nobody pauses the TV and reads that. But if you were to read that, it'd probably tell you somewhere in there how fast they were actually traveling when they garnered that maximum miles per gallon. Does that make sense? And I guarantee you, when it says miles per gallon on the highway, that nobody is saying that their car at 70 miles per hour is getting those miles per gallon that they're demonstrating or they're giving you. Does that make sense? Okay. So how do we tell that stuff? How can we be certain about it? Because they can't lie. Okay. So there's government regulations. Volkswagen got in trouble. They weren't doing it with miles per gallon, but Volkswagen was talking about it was their EPA issues, but they're talking about their emissions. Okay, and they were fudging their numbers on their emissions a couple of years ago and got in a lot of trouble for that. Okay, a lot of financial trouble because they were fudging their numbers. So there's governmental rules that say you cannot lie in your marketing, okay? But as long as you present in that small print somewhere what your maximum miles per gallon was generated from, what speed, you're good, okay? And that's something you guys will talk about, statistics, how they can use statistics, how they can use data to kind of sway people's decision-making skills, sway your emotions. If I see 32 miles per gallon and my car gets 18 right now, maybe I'm in the market for a new car then, okay? And they sway my emotions. But what I need to understand then is that when I go drive that 32 mile per hour car, 32 mile per gallon car, at the speed that I drive my 18 mile per gallon car, I might really only see maybe a 4 or 5 mile per gallon difference, because what they were marketing to me was not the speed that I traditionally drive. Does that make sense? Okay. So where do they get this? That's the part that I was always concerned about in school. Okay, I could do the math, I could do the opposite of BO2A garbage, but where do they get this? Garbage. Okay, do you know where they get this? Because you did it last year. And that's the thing about high school math. I didn't piece that stuff yet. I didn't make connections between last year and this year and next year. Okay, but once you start making those connections, math is so much simpler. Okay, I think all too often we believe that our math courses are kind of standalone things. Okay, where if we can see at the continuum, it makes us it allows us to piece things together and makes the system a little bit more easy to use and manipulate the way we want to. All right, so where do they get that? You did it last year. I'm just going to kind of look at this real quick. Okay, basically what's going on here is I've got down here across the bottom my independent variable. I'm going to say this is the speed that I travel. Okay, and that's going to be in miles per hour. This up here is going to be my capital M that the function talks about, and that's miles per gallon. And basically what they do, okay, Honda, you go down to Marysville, okay, Honda has a racetrack behind their facility, and they might do this type of thing on that racetrack, okay? You guys know what a dyno is? Anybody in the cars know what dynos are? Okay, so a dyno is essentially it's two big cylinders that rotate. Okay, and you put your front wheels on those, or if it's just a front-wheel drive or rear-wheel drive, you put whatever your driving tires are. So if it's all-wheel drive, you have two sets of these. Okay, but basically they rotate. Okay, so that when I put my car on top of those things, I can push the gas pedal down, and this car can start driving, but it doesn't go anywhere because those cylinders rotate. Does that make sense? So it's like a treadmill for cars. So what they do, either on a dyno or they might put it out on a racetrack, they might fill these cars up with a certain amount of gas. They control the variable of how much gas they use. Okay, and then they set let's say they set the cruise control to 12 miles per hour, and they let that thing run out of gas. Does that make sense? Okay, and then they calculate, well, how far did this thing travel until it ran out of gas? Take the distance it traveled, divided by how much gas is in it, we get a miles per gallon, right? So we got a speed, maybe let's look at this point right here. Okay, point I, a speed of 12 miles per hour, and it garnered us 3 miles per gallon. Does that make sense? And that's a data point. Then we take that car again, and we fill it up, and we set the cruise control to maybe 14 miles per hour. And at 14 miles per hour, we see we get 4 miles per gallon. Does that make sense? And we fill it up again. And we change the speed. And we keep doing that to collect these data points. Does that make sense, everybody? Okay. And as I keep increasing the speed, we start to see that eventually these miles per gallon are going up, right? Okay, so right here I'm at 42 miles per gallon, and I'm getting 42 miles per hour. I'm at 32 miles per gallon. Okay. As I continue to go through here, it kind of looks like the faster I go, the less miles per gallon I get, right? Think about engines. Okay. If I'm running my engine at 100 miles per hour, I'm going to consume gas pretty quickly. Okay. I don't maximize that gas potential in my engine. I lose that efficiency idea. Okay. So this shape here of these data points. And they would do this, guys, they would do this hundreds of times. And they would do it with multiple cars of the same model, okay? And they would collect all this data. So right now I've only got maybe like 20 pieces of data up there. They would probably have thousands of pieces of data to generate this, okay? But does that function, does that data look like it's quadratic? Does it look like I can fit a parabola in there?
Yeah.
Okay. You guys remember last year doing maybe things called lines of best fit? Remember having data, and you did this even in Algebra 1. You do it in science. If I had a line of best fit, so those are my data points. You guys remember trying to take, okay, let's take two of these data points, maybe this one here, and maybe that one there, and I use those to create that line. And what happens is that there are some points that are on that line, but there's some above it, and there's some below it, right? Call it the line of best fit, okay? Now, there are tools that tell us, okay, maybe I should have chose J, maybe I should have chosen H instead, or whatever. But there are things that we can use that kind of make us choose the best line of fit. And we call it least squares regression and that kind of stuff. Not going to get into that right now with you. But there is a tool, and it basically talks about taking these distances from these points to the line, all these points to the line, and trying to minimize that aggregate distance, and that will then give me the line of best fit, okay? But you guys did that last year. That's called linear regression. Remember hearing that phrase? Okay. Get rid of all those points. So right here, our data best fits a parabola. Parabolic, called quadratic regression. Does that make sense? We could have cubic regression. We have quartic regression. We can have exponential regression. All right? So when you plot your data, you can kind of visualize, okay, what is the kind of overall structure of that data? What's the behavior? And then fit a particular type of function to it. Okay? Well, if you remember from last year, this is how you did this. You chose 3 points, and I'm going to choose, I've already got them here set up in red, but let's put their numbers with them, the coordinates. Now, I kind of manipulated this so that I could use real nice numbers, okay? My quadratic regression might be different if we're doing this by hand, and I didn't tell you which points to choose. So if you thought maybe I could just look at any one of these points, any 3 of these points that I want to, and find a quadratic that goes through that, your curve might be different than your neighbor's, but one of yours is going to be a better representation of the data than the others. Does that make sense? I believe, and again, there are tools to tell us maybe I should have chosen maybe instead of A, maybe it would have been better, or instead of A, maybe I is a better point to choose, okay? But I chose A, B, and C because when I put in that curve, in GeoGebra here, that goes through A, B, and C. So any quadratic, there should be between any 3 points, there's always one quadratic that can go through them. Does that make sense? So any two points, there's exactly one line, right? Through any 3 points that are nonlinear, there's exactly one quadratic. Okay? So I chose those points to generate that quadratic. Does that make sense? Now I chose those. Does it look like some of my points are above that quadratic, some are below it, and then obviously some are on it, right? I think that models my data the best. Okay? Some of you might thought maybe just go poly, or I guess I go fit poly. Maybe some people thought, I, L, and R are the best. Okay, and that would give me that quadratic. Does that make sense? Okay. But there's a lot of different quadratics up there that are all kind of similar. They're going to have very similar coefficients. Okay. But I chose those 3. Okay. Like I said, there are tools that allow us to choose the best 3 that minimizes the distance that all of the aggregate distance that all these points are from that line. And you did that last year with quadratic regression. You guys remember getting on your calculator, going to Second. I think it's under vars. Y vars. No.
So that was under stat.
There you go. Thank you. You go under stat, go to calc, you see linear regression, quadratic regression, cubic regression, quartic regression, linear regression A plus BX, okay, exponential regression, power regression, okay, sinusoidal regression. But we've done this before, right? These functions on your calculator actually will use that process of trying to find the best points to choose, and it eliminates the human error, okay? But like I said, I'm going to choose these. You guys remember by hand last year, if you had anything, this is quadratic, so it's going to be of this form. Ax squared plus bx plus c equals your f of x. Okay? That's an x value. That's an f of x value, right? That make sense? Okay? Then that means this could be a times 14 squared plus b times 14 plus c equals 4. Did you guys agree with that? Plugging in x and f of x. The next thing you did was you came to this point. And you said, okay, well, a, and now x is 42, so say 42 squared plus b times 42 plus c equals f of x of 32. And then you went to this point here, did the same thing, got a of 70 squared plus b times 70 plus c equals 4. Okay? And once you set that up, you would take any two of these. So I may take these two. Okay? You would take those two, and you would eliminate the c term. Okay? I just multiply that bottom one by -1. Will that, when I use addition of two functions, then will I get rid of the c? That make sense? So I do that as a system of equations. So I'll eliminate c. So that means I'd have two equations with just a and b left over. I would then grab that one and that one, and I would eliminate c out of those. So now I have two different equations that have only a and b left. Well, now I've generated two equations that both have a and b in them, and now I'm going to go try to eliminate either a or b. And that would get me down to just solving for a or just solving for b, right? And I take that a that I found, and I plug it in to one of those equations that had only a and b left in it, and solve for the other variables. So now I have a and b. Well, now I know what a and b are. I'm going to take those two values and plug it back into maybe the yellow one up there and solve for c. Now I have a, b, and c. I have my constant and my coefficient. Does that make sense? Remember doing that?
Yeah.
And that was a long, tedious process, right? By hand. So then you were maybe shown how to use a matrix. Okay? So we use a matrix. Take your TI-83, 84 out. Okay? We go to second matrix. Go down to A. I'm going to edit it. Okay, I want a 3x4 matrix. I've already filled this in, but basically what you do, okay, is you put in your coefficients for your yellow equation there. So that'd be 14 squared. That's my 14. C had a coefficient of 1, and then equals 4. And I do the same thing for the second one. Okay, so that's 42 squared. That's 42, 1, and 32. And then I've got 70 squared, 70, 1, and 4. Then I go second matrix, and I go over to math. Oh, not that one. Yeah, okay. So I go down to second matrix. I go down to, I go over, I think, to the calc part of the matrix, and I go find the RREF option. Okay? And RREF, you guys remember what that stands for? REF? No. Which is row reduced echelon form. Ever heard that?
No.
A reduced row echelon form? Sometimes you see it row reduced, sometimes you see it reduced row. You ever learn about Frederick Gauss?
Nope.
Oh my goodness. Okay, so the guy one of the most influential, most important mathematicians of all time for algebra was named Frederick Gauss. Okay? The elimination that we do, you guys talk about elimination, substitution with systems, right?
Yeah.
Frederick Gauss is responsible for the elimination process. Okay? A lot of times called Gaussian elimination. Okay? He's the one basically realized that when we're able to multiply any equation by any number that we want to and add it to any other equation to essentially get the ability to solve for A, B, and C. Okay, to solve for our variables in a system. This is called the identity matrix right here. When we have ones across that diagonal, and when that happens, this is telling me that is 1A. This is telling me 1B, and this is telling me 1C. So 1A equals that number, 1B equals that number, and 1C equals that number. So that's negative 128 as a decimal, or as a fraction. Okay? So that is then where this comes into play. Does that make sense? That's how they generate that formula. And I think that took a lot of time to talk about, but I think it's important for us to understand that when we're doing our homework questions, and they give us something like that, they're using collected data to generate that. Does that make sense? And it's not something that you guys are unfamiliar with. You learned how to do that last year, but I don't know if you connected the dots to what you learned and then what you see in homework problems, what you see being modeled in these real life situations. Does that make sense? Okay. Okay, so the goal here then is, can we figure out at what speed do we maximize our miles per gallon? Okay. Well, at what speed? At what speed do we maximize our miles per gallon? So in my parabola, I'm looking for what point? Yeah, I'm looking for that maximum point right there. Okay? Because that's going to be the speed that gives me the largest y value back, right? Okay? So, how do I find the vertex knowing that? What's the easiest way? Yeah. My independent variable, s, is equal to the opposite of b over 2a. So it'd be negative 3 over 2 times negative 128. Ends up giving negative 3 over negative 114. Ends up being negative 3 times negative 14, which ends up being 42. That's the s. That's the independent variable. Okay? That is not the maximum. Does that make sense? That is the speed in which the maximum occurs. That is the speed in which the maximum occurs. The maximum is always the y value. Okay? What was the maximum miles per gallon that I earned? Well, that means then I got to take that 42 and plug it in. It means I have to do that. Does that make sense? When you evaluate that, you get 32. Okay? So what that's telling me is that if I travel 42 miles per hour, I'm going to earn 32 miles per gallon. That's the most efficient that this car is. So when you see that on a commercial, it's going to say, we get 32 miles per gallon on the highway, but who in here is going to go on the highway and drive 42 miles per hour? Right? So even though it's true data, it's true information, it's a little bit misleading, isn't it? Mm-hmm. Okay? So those are things to kind of maybe understand as a consumer. Okay? Knowing that stuff allows you maybe to make better decisions as a consumer. There's some questions in your homework. I'm just going to do, kind of going off of memory here. I think it's question 13. Start talking about like a manufacturer is making, they generalize it really terribly. They call it, they're making a commodity, or selling a commodity. Okay? So plug in anything you want, a commodity being maybe
Banana.
bananas, maybe it being cars, maybe it being whatever. Okay?
$50.
And they say the revenue, you guys know what revenue is?
Yeah.
What's revenue?
Like, extra, amount of sales.
You said you knew what it was, and that means you knew what it said.
The money you get back, like,
So is revenue equal to profit?
Yes.
Then why do we have two words for it?
To confuse it.
Revenue is just the money brought in. Okay, so let's say that we, let's say, like McDonald's. We're tracking today's revenue for McDonald's. That is just the money that McDonald's is collecting from the customers through the day. Does that make sense? That's not profit. Because what does McDonald's then have to do? They have to pay people, right? They have to buy the food first, right?
Yes.
Okay? So then those are their costs, correct? Revenue, remove your cost from it. What's that generate?
Profit.
Profit. Okay? So revenue is just kind of the gross amount of money that you bring in. Profit is the net. Okay? When you do the subtraction of your cost. Okay? So that's what this is. This is, and every business does it. So we use P&G. We use P&G in the last class. Let's say the commodity is we're making Tide Pods. Okay? and I know through the use of Tide Pods, I understand that I can bring in a particular revenue per Tide Pod. Okay? And this is something that you guys will learn, and like if you take a business calc class, they talk about marginal cost, marginal profit, marginal revenue. Basically, think about this: if we were P&G, if you owned P&G, and your number one goal was to build Tide Pods, to make Tide Pods and to distribute those. Okay, you have to build the building, you have to pay the mortgage of the building. Okay, you have to pay to put all the machinery in there to make the Tide Pods. You got to pay the employees. You got a mortgage. Okay, you've got warehouse room that you've got to pay for. You've got a lot of overhead in regards to like insurances and that kind of stuff. Would you guys agree that if I made only one Tide Pod, that would be one very expensive Tide Pod? Okay. So when I'm talking about like what we call marginal cost, making one Tide Pod would be millions of dollars. If I make two Tide Pods, doesn't that millions of dollars get cut in half? And now that first Tide Pod takes half of that cost, and the second Tide Pod is worth the second half of that cost. If I make three, doesn't it cut it in thirds now? And each one of those Tide Pods is now a little bit less in cost. Okay? But what if I make 100 million of those Tide Pods? Now, each one of those Tide Pods is a little bit smaller, right? Maybe the cost of each Tide Pod then is only like fractions of a penny. Okay? What we find out through calculus is we can determine how many Tide Pods we need to make to where we can essentially break even. Okay? And how many Tide Pods, and if I make 100 million, maybe I maximize my profit with 100 million. But 100 million to one, I don't maximize my profit anymore. That make sense? So if I don't maximize my profit anymore, why make the 100 millionth in one? Okay? Just stop at 100 million, right? Does that make sense to everybody? So those are places that we can use mathematics to kind of help us make decisions. I don't want to just start making as many Tide Pods as I possibly can and there not be a market for it. Okay? Because now I've made a lot of Tide Pods that were really expensive, and now they're sitting in a warehouse that I had to pay a mortgage on the warehouse. Okay? So it allows us to make those types of decisions, and this is kind of the basis of that. This is the start of that. Okay? We've got some commodity X, and we want to figure out what is the maximum revenue I can make from X. Okay? Well, this thing here is going to be, there is no C term, so it's going to be a parabola that kind of looks like that. That is my X. That is my R of X. That's my revenue. Okay? What I need you to understand here is this A, 100, is that my A term, A coefficient?
No.
No. What's my A coefficient?
4x squared.
Yeah, that's 0.4. Okay?
0.4 x squared.
So all of that is better written as negative 0.4 x squared plus 100x. So now when I find the opposite of b over 2a, I'm going 100 over negative 0.8, and that gives me 125. Does that make sense? I've been working with some people, and they're not paying attention that ax squared plus bx plus c, the a, the b, and the c are attached to the x squared, the x, and the x to 0 respectively. Okay? So we need to make sure that we address that. Now, that is also, the next mistake that I'm seeing is that they think that's the maximum. That's not the maximum.
Nope, that's not the one.
That is where the maximum occurs. That is the number of commodities, maybe the number of Tide Pods that I have to make to maximize my revenue. Okay? Maybe that's the number of customers that I have to serve as a McDonald's employee to maximize the revenue that day. Okay? So that right there is 125. So the maximum, though, the largest revenue that I get back is taking that 125 and actually plugging it in. And I think that gives me like 6250. It might be 6520. I can't remember if it's 2 or 5, what order they come in. But that's the idea. Does that make sense? Okay? That is the maximum. The maximum is a Y value. Okay? The vertex is the ordered pair. The maximum is in the Y value of that ordered pair. That's something we can do?
Yeah.
Okay. No.
Is there gonna be more?
About 11 minutes.
Is there gonna be more work tonight?
No.
Oh, we should play.
I know.
Oh, we have homework tomorrow. They gotta get your food.
Yeah.
Really?
Yeah.
Yeah. We're going to not every day.
All right, so I want to start a little bit on 3.2, okay? Now, understand, guys, that obviously these are sections of 3.1, 3.2, but it's all continual, okay? So it's not, when we go to 3.2, we're not talking about something completely new. This is all kind of easy flow type thing. Maybe we talk about chapter 3. There probably shouldn't even be sections because it's all kind of progressive, okay? When we talk about polynomial functions, you don't need to write that one down. Let's look at this one. You don't even need to write this down. Because I think these are things you know. Okay? If I look at that polynomial up there, obviously we know what our coefficients are, right?
Yeah.
We know our constant is the term that has no variable, right? It's actually x to the 0 is the variable that sucks that -6. That's my constant term. The degree is the largest exponent up there. Okay? So we call this a 5th degree polynomial, sometimes called a quintic. Okay? Leading coefficient, leading term. Okay? That's what I really want to talk about here. Is that, I want to use that terminology, leading term, leading coefficient. You might hear me say dominating term. Okay? Let's think about this. If I were to graph, now I'm not going to be able to remember all of those coefficients, but let's just say I graph 3x to the 5th plus 3x to the 4th minus 2x squared plus x minus 6, something like that. Okay? So that's maybe that cubic function, right? Does 3x to the 5th look very similar to that? Yeah. The only difference is when x is kind of in the ballpark from -1 to 1, right? Everywhere else, that thing looks almost identical. These two lines are almost the same thing, right? These curves, okay? Well, what that means to us is that this function here, 3x to the 5th, that leading term dominates, meaning that the other things do play a role, but they're a marginal role. They're a very minute amount. Think about this. If I take x to be 100, x to be 100, and I put it into that 5th power, 100 to the 5th power. So it's going to be 10 zeros, isn't it? Okay. Think about a number with 10 zeros. What is that? It's 10 billion, isn't it? Okay. 10 billion. So multiply that by 3. I got 3 billion here. Okay? Sorry, 30 billion. Put 10 in there. Or sorry, put 100 in there. So now I've got 8 zeros, right? Okay? Well, 8 zeros is only, what, 100,000? No. So, yeah, sorry, 100 million. Okay? Well, 100 million times 6 is 600 million. It's a lot. But 30 billion is so much more. Does that make sense? If you understand the difference between 1 million and 1 billion, 1 million in terms of seconds is about 11 days. 1 billion in terms of seconds is 31.5 years. Okay? So compare 600 million to 30 billion. That 30 billion is huge compared to the 6. Does that make sense? So that's why we call that the dominating term or the leading term. It's very important for a lot of things that we're going to do here in the next couple of days. Okay. That term allows us to make some arguments about a particular relationship. So I'm going to create just some generic function x to the n, and I'm going to let n be an odd number. So I'm going to start at 1, I'm going to go up to 11, and we'll go increments by 2. So that should keep that to be an odd number. Good. Okay. And I want to look, let's say if x is greater than 1, let's plot f of x. And if x is less than -1, let's plot f of x. So what I'm doing here is just a tool to help me color some stuff. So we can talk about some components of these graphs a little bit quicker and easier. Okay. So I've got this. This is a linear function, right? Okay. It's considered a power function, x to the first power. But as x goes to positive infinity, as x moves along the x-axis to positive infinity, can you argue what your y value is going to be doing? What's your y value going to do as we go to positive infinity? It's increasing to what? Infinity, right? Does that make sense to everybody? As I go to the right, go to positive infinity, y is going to positive infinity. As I go to the left, as x goes to negative infinity, where's y going? Negative infinity. Does that make sense? That relationship, that's the most simplistic way of looking at it. That relationship is what we call end behavior, END behavior. It's showing what the graph is doing in the long run. Okay? Now, where it's orange, there's going to be maybe some discrepancies, some issues that we have in algebra because we don't have the calculus yet to really determine what's going to happen in the orange for these next types of functions, meaning like an x cubed. Okay? The orange right there, we're not 100% sure what's going on. Okay? It can do several different things, and we'll talk about that a little bit tomorrow. But look at the blue. As x goes to positive infinity, is the blue in the first quadrant going to go in the y value to positive infinity as well? Make sense? So here's my question. Does that function and that function have the same end behavior? Are the y's doing the heck? Are the y's doing the same thing as the x's go to positive and negative infinity? Okay. What about these two? Are those the same behavior? Okay. What do we say? That's x to the fifth, right? What about these two? Are they showing the same behavior in the blue? Yeah. Are all of these x to the third all the way to x to the 11th, are they showing the end behavior? Okay, so if I gave you x to the 21st, you've never seen x to the 21st. If I ask you as x gets really, really, really big in the positive direction, can you tell me what the y value is doing? Getting really, really big in positive. So as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to negative infinity. Does that make sense to everybody? Okay. That is, though, that is only if this number out in front is a 1, right? Okay, now think about this. Let's put a 4 out there. Did that change any of that behavior? Did that 4 out front change what the blue is doing? No. So that coefficient, whether it's 1 or 4 or 12, it doesn't change what the end behavior does. It just speeds the end behavior up. Does that make sense? It makes me get to those larger y values quicker, but I'm still going to get to infinity. Okay? Let's do this. So that's a vertical stretch. What if I make my y value, or so my a value negative? What's a negative outcome of a function going to do? Over the x-axis. So when I flip it over the x-axis, doesn't that kind of reverse the way we think about the end behavior?
Yes.
So now as a is negative, okay, when I go to positive infinity on the x-axis, the y's are going to go to negative infinity, right? As x goes to negative infinity, the y's go to positive infinity, correct? And as I keep changing that, does that behavior then stay the same? Okay? So you don't need to write this down yet. We'll write this down tomorrow. You can find it. Okay, we're going to go through and kind of write something down like this. But we see right there, and this is those first two graphs there, are talking about a power that is odd. Okay? Because P has odd degree. If A is positive, you're going to have that first graph. And the end behavior of everything A being positive, x to an odd degree, is going to look just like that first graph. Now, where it's got the dotted part of the curve, that's where there's ambiguity. That's where there's some different things to happen. But the end of the curve, we know exactly what should be happening. Does that make sense? When A is negative, we get the second graph. Okay? And then the last two graphs then are the same idea, but instead of being an odd degree, they're even degrees. Okay? So that's what we're trying to investigate here. Well, the idea is if we're going to learn something about a cubic, it tells us something about a fifth degree, seventh degree, ninth degree, 11th degree, whatever. If I can know something about a quadratic, it tells me things about fourth degree, sixth degree, eighth degree, and a lot of those things carry over and are very easy to determine once we know our foundational quadratic and cubics. Okay? The idea is, and the reason we do it this way, is it allows us not to have to remember what x to the fifth by itself looks like, what x to the sixth by itself looks like, what x to the seventh by itself looks like, because eventually that's an infinite number of functions, right? We don't want to have to memorize an infinite number of functions and what they look like. If we see relationships that are shared, it allows us to really learn two functions, and then the shared relationships to kind of extrapolate and determine the other function. Okay? So that's kind of the plan on the next couple days, to kind of investigate those relationships. Okay? No new homework. The homework has been extended until tomorrow evening. Okay, so make sure you finish that up. Have a wonderful day.